You know, we're always trying to build things better, faster, stronger, more efficient. But what if there's a hard stop? A fundamental law of physics that basically says, look, this is as good as it gets. Well, today we're digging into exactly that, the unbreakable rules that dictate how we get work out of heat.
So let's start with the big question. Is there a speed limit for efficiency? It's a pretty wild thought, right? I'm not talking about how fast a car can go, but a universal speed limit on how well any engine, from a steam train to a nuclear power plant, can possibly work. And it turns out, the answer is a huge, definite yes.
And that really kicks off this whole quest for efficiency. For centuries, this has been the puzzle that has kept engineers and inventors up at night. How do you get the most possible work out of heat? How do you take the energy from burning fuel and turn it into motion without just wasting most of it?
Okay, so to figure out the limits in the real world, you actually have to start by imagining something that's, well, not real at all. Let's talk about the perfect engine. No, you can't build one. This is a thought experiment, a blueprint for a machine that has absolutely zero flaws. What would that even look like?
The answer to that question comes from something called Carnot's theorem. And this, right here, is the absolute core of our whole discussion. It's a principle that just lays down the law. It tells us the absolute, tippy-top, maximum possible efficiency any heat engine can ever have.
So you can basically think of all engines in two buckets. In one bucket, you've got the ideal, the reversible engine. This is our fantasy machine, right? No friction, no heat leaking out, nothing is wasted. And in the other bucket, you have the irreversible engine. That's reality. That is every single engine ever built, all of which always lose some energy to the real world.
Of course, if you're going to have a perfect engine, you're going to need a perfect fuel. The stuff that actually does the work inside, the working fluid, would have to be something called an ideal gas. It's a totally hypothetical gas where the particles have no size and never interact. It's just another piece of this perfect puzzle that can't exist in our world.
Okay, so all this talk about a perfect engine has been building to one massive point. There is an unbreakable limit. Because we've defined what perfection would look like, we can now understand exactly why it's impossible, and what the actual ceiling for efficiency really is.
And here it is, the law of the land, written as a surprisingly simple equation. Now, don't let its size fool you. This little formula dictates the performance of every single heat engine in the entire universe. Efficiency, that's the funny little eta symbol, is just 1 minus the ratio of two temperatures. So what are these two temperatures? Well, T1 is your hot source. Think of it like the fire roaring under a steam boiler. And T2? That's your cold sink. That's the cool air or river water where all the useless leftover waste heat gets dumped. And here's the absolute kicker, the most important takeaway. The maximum possible efficiency of an engine has nothing to do with how clever its design is, what materials it's made of, or what fancy fuel it burns. It depends only on the temperature difference between its hot side and its cold side. That's it. That's the unbreakable rule.
And let's put some real numbers to this. If your hot source is 600 Kelvin and your cold sink is 300 Kelvin, the absolute best efficiency you can ever hope for is 50%. Period. But if you can make that fire hotter, crank it up to 1,000 Kelvin, suddenly your maximum possible efficiency jumps to 70%. The bigger the temperature gap, the more efficient your engine could be.
All right, now for a really cool twist. So far, we've talked about using heat to create work. But what happens if you flip the script? What if you put work in just to move heat around? Welcome to the wild world of engines in reverse.
And this isn't some weird abstract idea. I'm willing to bet you have at least one of these reversed heat engines in your home right now. Your heat pump? Your refrigerator? Yep, both are perfect, everyday examples of this exact principle.
So how do they actually pull this off? Well, it's the complete opposite of a normal engine. You put work into the system. That's the electricity you're paying for. The machine then uses that energy to literally grab heat from a cold place, like inside your fridge, and dump it into a hotter place, your kitchen. It's forcing heat to flow against its natural direction, from cold to hot.
So how do we grade them? We don't use the word efficiency. Instead, we use something called the coefficient of performance, or COP. But look closely at those formulas. They should look a little familiar. They're made of the same exact ingredients, our old friends T1 and T2. It's the same fundamental physics, just rearranged for a totally different job. So the Carnot cycle gives us this perfect theoretical gold standard. But how do the messy, real-world machines we actually build stack up?
To figure that out, we've got to look beyond the ideal and check out some real-world engine cycles.
Let's take the diesel cycle, for instance. This is a model of what's really happening inside a diesel engine. And unlike that clean, simple Carnot cycle, this one is messy. It has to account for the complicated reality of explosions and combustion, with all kinds of different pressures and volumes changing all the time.
And remember that high-temperature source, our T1? In the real world, that's not just a number. For a lot of big industrial steam boilers, that temperature is created by burning something very specific, non-coking bituminous coal. The type of fuel you choose is a real, tangible part of the efficiency puzzle.
And it's not just the fuel, it's the working fluid too. Remember the ideal gas from our perfect engine? Real engineers have to use real gases, and they all have their own quirks. Hydrogen, for example, has the lowest molecular mass of any gas, which totally changes how it behaves under heat and pressure. Mastering these real-world details is how engineers try to get as close as they can to that ideal limit.
And finally, it's so important to remember that not all real-world engines are even playing the same game. A simple gas turbine, like in a jet engine, actually has a pretty low efficiency-to-work ratio. And why is that? Because it wasn't designed to sip fuel. It was designed for one thing, creating a massive amount of power. It's the perfect example of the trade-off engineers always have to make, raw power or maximum efficiency.
Which leaves us with one last big question to chew on. If there really is a perfect, unbreakable limit to efficiency baked into the laws of physics, what does that mean for our future? Does it mean that one day technological progress will just hit a wall? Or does it just change the game, making the challenge all about how ingeniously close we can get to a perfection that we know we can never truly touch?